When we talk about the infrastructure of artificial intelligence, we are talking about the plumbing that makes the magic happen. For a long time, the machine learning community operated on a specific model that treated data as a stream of independent events. This is the foundation of traditional machine learning. In this environment, the system takes an input, processes it through a model, and produces a score or a classification. Once that calculation is done, the system forgets. It is stateless. Think of it like a factory assembly line. A part comes down the conveyor belt. A sensor scans it. A robot arm makes a decision based on that scan. The part moves on. The machine does not need to remember what the part looked like 5 minutes ago to make the decision on the current part. The infrastructure for this is built around efficiency and throughput. We rely heavily on central processing units to handle the logic. We batch the data together to maximize the usage of the hardware. We store the models in a database and load them into memory only when a request comes in. This works beautifully for fraud detection, spam filtering, or recommendation engines where the context is usually self-contained within the immediate input. However, the landscape has shifted dramatically with the arrival of large language models. These systems do not operate on a stateless pipeline. They are fundamentally stateful. When you ask a question to a modern AI assistant, the system must remember every word you have said in that conversation up to that point. This context is not just a detail, it is the core of the intelligence. This changes everything about the infrastructure required to support it. Here is the thing. In traditional machine learning, the model is the only source of truth. In large language models, the model is a reasoning engine that needs external memory to function effectively. This is where the infrastructure diverges significantly. A traditional model fits into a standard graphics processing unit memory slot. It is static. A large language model, especially when running at scale, requires vast amounts of random access memory to store the context of the conversation. This is known as the key value cache. It grows linearly with every token generated. If you try to run a massive model on hardware designed for traditional machine learning, you will find that you run out of memory very quickly. The bandwidth becomes the bottleneck. This leads us to the architecture of retrieval-augmented generation. This is a method where the system does not rely solely on its internal weights. Instead, it queries an external vector database. Imagine a library where every book has been converted into a list of numbers. When you ask a question, the system searches this library for relevant passages. It brings those passages into the context window of the model. This allows the system to answer questions about data it was not trained on. But this adds a layer of complexity to the infrastructure. Now you need to manage the vector database. You need to ensure that the retrieval process is fast enough not to add latency to the user experience. You need to handle the embedding of new data so that it can be found later. Consider the scaling implications. In the stateless world of traditional machine learning, scaling is horizontal. You can spin up more servers to handle more requests. If one server fails, another takes its place without losing any state. This makes load balancing straightforward. In the stateful world of large language model inference, scaling is often vertical. You need more powerful hardware with more memory per instance to handle the context window. You cannot simply split a conversation across multiple servers easily because the state is tied to that specific session. This requires specialized orchestration tools that understand the nature of the workload. Furthermore, the cost structure changes. Traditional machine learning pipelines are often CPU-bound and can be run on commodity hardware. The inference of large language models is almost exclusively GPU-bound. The cost of a single high-end graphics processing unit is significantly higher than a standard central processing unit. This means that the economics of deploying these systems are different. You are not just paying for compute time. You are paying for memory bandwidth and storage, I/O, to feed the vector database. Another critical difference lies in the latency requirements. In a batch processing pipeline, you can wait minutes or even hours for a result. In a conversational interface, the user expects a response in seconds. The infrastructure must be optimized for low latency. This means keeping the model weights in high-speed memory. It means minimizing the distance between the storage and the processor. It often requires specialized hardware that is designed specifically for matrix multiplication rather than general-purpose logic. This shift in infrastructure means that the skills required to build these systems have also changed. Engineers who were comfortable with batch processing and distributed computing now need to understand memory management and GPU architecture. They need to understand how to optimize the retrieval process so that the vector database does not become a choke point. They need to think about how to manage the state of the conversation without overwhelming the available resources. The transition from stateless to stateful is not just a software update. It is a fundamental change in how we approach the problem of automation. We are moving from systems that categorize the world to systems that reason within it. This requires a different kind of plumbing. It requires a focus on memory, on context, and on the speed of retrieval. As we look at the future of this technology, the infrastructure will continue to evolve. We will see more specialized chips designed for these specific workloads. We will see better ways to compress the context windows so that we can fit more information into the same memory. But the core principle remains. The difference between a traditional machine learning pipeline and a modern large language model inference engine is the difference between a calculator and a conversation. One processes numbers, the other processes meaning, and the infrastructure must support that meaning without breaking under the weight of the context. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.